Okay, so ready to go?
Yep, go to Minicam. There, click on full screen, and maximize it. There you go.
Okay, welcome back everybody. So just to remind you where we were, so we had these upper two rows of this diagram that summarizes Chabauty's original method, and we want to rephrase it in a way where there's no more J. So we started by defining the QP Tate module, which we called V, and we showed that we could define that in terms of the étale homology of the curve. So that's good. And so now I want to relate the rational points to these Galois cohomology groups by sort of a fancy version of Selmer groups and the descent map. So okay, so let me start going through this. So let me just remind you of some classical stuff. So so you start by writing down the Kummer sequence for this Jacobian, where you have multiplication by p and then you have its kernel, which is there, and then if you take Galois cohomology of this, you get J of k going to take this on the h zeros, and then it goes on to the first h1, the h1 of the Galois group of k acting on the J bracket p. And then you can, if you want, you can contract that into, on the left, you can just write that as J of k modulo P J of k included into the H1. And so, I mean, so classically people were doing this in order to try to prove the Mordell-Weil theorem, to bound this. And that's sort of the first step in proving that J of k is finally generated, to bound this, to prove this is finite. And well, it'd be really nice if you could prove this was finite, because that would make this finite too. But this, unfortunately, this one is typically infinite dimensional. It's an infinite dimensional FP vector space. Well, okay, I mean, well, it's not always true. I mean, okay, if the dimension is greater than 0, then it's true that this thing is infinite. Okay, so but it's okay. So the next thing you could try is, okay, maybe it's infinite dimensional, but maybe you can somehow figure out where inside this infinite dimensional space. Maybe you can find some finite dimensional subspace that bounds this, or at least figure out which of these classes here actually come from here. Now that's hard to do directly, but so the idea is to look not directly at what's in the image, but look at what's in the image locally. So you can draw, so for that you draw the same picture, but for every completion of k. So V is some place of k, and then you can take the local field, which might be Archimedean, maybe not. And you could just do the same thing, because this argument didn't really use anything about the field, except maybe this, Okay, so you just write the same thing, H1 now KV J bracket P. And again, this includes into there. And and these are this functorial in fields. So you have maps going this way, and so then you can see that in order for something here to be in the image, it must also map down into this image, just from the commutative, because you could have gone around the other way too. And so that gives you a condition for every V on which classes here can come from here. And if you impose those conditions for all V by writing direct products here, then you get what's called the Selmer group. So the Selmer group it's a subgroup here. It's a subgroup of the global cohomology. So I'll write it as the P Selmer group. So it's a subgroup that contains the image of this quotient of the Mordell-Weil group. And I mean, it's not the classes here that are locally trivial. They're not the classes that map to 0, but they're the classes that map into the local image. That's the definition. So okay, so if I actually want to write this down, I would probably say, well, let's see, I'd put an alpha. If I give these maps names, let's call this one alpha and beta. So beta is just the restriction map. So then by definition, this Selmer group. Sorry, Selmer group of J. By definition, it's the set of cohomology classes such that when you map them down, you land in the image of the local in the image of the local points. And the whole point of this is that this group turns out to be this group turns out to be, well, this turns out to be finite, and even better, it's also computable, at least in principle. And so that gives you, in fact, this gives you the only known way to bound ranks of abelian varieties over a number of fields. So yeah, every other method sort of boils down to this argument in one form or another. So that's known so far. Okay, and you can do this not just with the p, multiplication by p, but you can try to get more information by repeating this with powers of p. And so similarly, you get well, you get j of, so here you get this quotient embedded into the Selmer group here, but now you can do j of k mod p to the n j of k, and that will be embedded into a higher Selmer group, a p to the n Selmer group of j, which is going to be contained in the global Galois cohomology of j bracket p to the n. And then you can take an inverse limit, and so then you get the p-adic completion of the Mordell-Weil group, and that will embed into the inverse limit of these guys, which I'll define to be, I'll just call it the ZP Selmer group. I mean, you can also take direct limits, which often is done in Iwasawa theory. But for this, I'm going to take inverse limits. So this is a ZP module, and this is going to be contained in the inverse limit of these things, which is again by definition or by, well, or by, yeah, that's going to be the Galois cohomology of the Tate module. Where here now we're really talking, actually throughout we're talking about continuous group cohomology. So you need to, these are represented by continuous cocycles. Okay, and then again, if you don't like rings that aren't fields, you can invert P, and so you can now get J. You can take this thing and invert P, and then that'll embed in, well, by definition, I localize this ZP module. I'll get what I'll call the QP Selmer group, which is then contained in H1 of K comma V. Okay. All right. So yeah. So this was just, yeah. These steps here were just inverting. This was just inverse limit, and this was invert P. Okay, so now, well, I guess I want to say, you'd like to say something about the error between, these Selmer groups are upper bounds for this, but how can you say what the difference is? And the difference is going to be sort of the obstruction, the thing that's preventing you from computing the Mordell-Weil group, that's given by some piece of the Shaffer-Average Tate group. So, classically, you have an exact sequence where you have the group that you're trying to compute, and then you have the thing you can actually compute, the P Selmer group. This is just the basic one, and then the error in your upper bound approximation is given by the P torsion in the Tate Shaffer-Average group. So. Yeah, so this is so this group here is the Shaffer-Average Tate group. Okay, maybe I won't write the definition right now, but yeah, so that's the Tate Shaffer-Average group of J. And and if you do, you can write down the same sequence for P to the n, and you can take inverse limits as blah 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 blah, and you get the same. So you can get an analogous statement for this fancier version. So going back to this last line, and now I can measure. So we said the P torsion in Schaub measures the difference between these two, and similarly there's going to be something that measures the difference between these two, and that's going to be given by this exact sequence where I have the p-adic completion localized at P to make it a QP vector space, mapping into the QP Selmer group, and then that goes on to, well, Well, which is just whatever you get. It's the inverse limit of all the p the n torsion in SHA, and then you take that whole thing and you make it into a vector space. And that's what it is. Now, but one nice thing happens. Well, it's conjectured that this SHA is finite. And if that's true, then these groups are not getting bigger eventually when n grows. And the maps in this inverse system are multiplication by p. So if these groups are not getting bigger, then any term in this inverse limit, that must actually be 0 because it's going to come back from way back here. It's going to get multiplied by a lot of p's. And so anyway, so this whole thing is conjecturally 0. So this whole thing is 0 if this SHA is finite, or more generally, if the p primary part of SHA is finite. So that's what's supposed to happen. So that means that in this limiting version, you actually this summer group is actually measuring exactly what you're trying to measure. Because I mean, this is going to be a QP vector space of dimension equal to the rank, the Mordell-Weil rank. And so the summer group should be the same thing, have the same dimension. Okay, so that's what I want to say about summer groups. Now, but you might say, oh, but this is bad because you still have J's on this paper. There are J's all over the place. And so we want to, I mean, going back to our diagram here, we want to do something. I mean, so I've defined this map here, and it maps actually into a sum group. In fact, maybe I'll put maybe it's time to actually draw the summer group into the diagram. Sorry, hold on a second. Yeah. Okay, let's put a summer group in here. So so the summer group is the QP summer group, and it fits in between here. It's the QP summer group of J. And so this thing maps into this this sort of descent whatever co-boundary map that goes from here to here, but it actually lands in this subgroup. So okay, so I can put things here. And I guess I could do something similar here. I could put, well, I mean, this also maps down to here. And and there, I guess I could put a horizontal map here. I'm saving a little bit of room because there's going to be all kinds of stuff that goes in here. So, because I still have J right here, and I want to get rid of. I want to have some this. I mean, it's good because this is getting. At least I don't have. I mean, this thing doesn't. Well, okay, it still involves J. That's the problem. So, okay. So what am I going to do next then? I want to give you another way to describe the summer group that doesn't involve J, because that really just depends on the p the n torsion in J for all n, because we already showed that you can express the p the n torsion of J just in terms of x. Okay, so this is so what's coming next is the ideas of Bloch and Kato. This is the Bloch-Kato summer group that I now want to explain. So let me do this. Okay, so Bloch-Kato's. So this is an alternative way of defining this sort of QP summer group that does not actually use the J. So it's going to be solely in terms of V, not J. Okay? So that's the, yeah, so that's, this probably should have been blue. This is like the section title. All right. All right, so let me start with instead of talking about this particular V that came as a QP tape module, let me just talk about a general Galois representation. So in the general setting, I'll have I'm going to start with, well, let's first start with a local Galois representation. So by this, what I mean, so is I start with my V is going to be a fine dimensional vector space, a fine dimensional QP vector space, but it's a representation, so it also has an action of a Galois group, and so it has a continuous action of some Galois group, and this is a local Galois representation, so it's going to be a local Galois group. It's going to be the absolute Galois group of one of these local fields, like KV. Yeah, so that's the Galois group of KV bar over KV, and okay, so that's my V, and Well, then there's this horrible thing called the decris. All right, so which is defined in terms of an even more horrible thing called bcris, and which I'm not going to try to define that for you, but it's some big ring defined by Fontaine, and so but once you have it, it's some. So what is it? Okay, so and then you take Galois invariance of that. So okay, so. Well, I'm not going to say too much about what this is. I mean, there's some definition in terms of Witt vectors, blah 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 blah, and then so it's a certain ring. Okay. I mean, it's not mysterious what it is. It's just that you don't want to actually see the definition. So, okay, it's equipped with, but it comes equipped with a Galois action. So equipped with an action of this local Galois group. Okay, and once you have that, then you can let the group act diagonally on this tensor product, and then you can take the variance, and this will give you some. This invariant will give you some KV vector space, and then it's a fact that this thing, the dimension of this vector space you get out of this functor, is always at most the dimension of the original representation as a QP vector space. And yeah, so that's a fact. And then, well, if equality holds, then you call V crystalline. So if equality holds here. If equality, holds. And maybe just to give you a sense of what kind of condition this is like, maybe I'll just mention another fact. So if you start, okay, so this is sort of a side comment here. So if you start with if you fix the V, and if you start with an abelian variety, and an abelian variety J, I'll call it J, even though maybe it doesn't even have to be a Jacobian, but it'll be over a local field now. So maybe you know the criterion of Narrow-Ogschaft-Ravitch for when a variety has good reduction in terms of its Tate module. So you can test whether J has good reduction if and only by looking at its Tate module. So it has good reduction if and only if it's QP. You can look, say, at the QP Tate module. If it's QP Tate module, which is the thing I often call EV, is, well, I mean, when you stay away from the residue characteristic, in other words, then it's just a question about whether this Tate module is unramified. So you can test good reduction by asking whether this V is unramified. That's for V not dividing P. But then you can ask, what's the right condition if you're at a place where V does divide P? And the answer is this crystalline. I mean, in this case, if you're over a local field of residue characteristic P, and you take the p-adic Tate module, then it will be ramified usually, but it will be not too bad, and that's what crystalline means. It's not too bad. So that's a sense that's an idea of what. Okay, so that's one way in which these crystalline representations come up. Okay, but we're going to use them for something slightly different. So we're going to look at. Let me give you one other definition. So now let's suppose that instead of a representation, we just have a cohomology class. In this, so V is again, I'm in this general setting where V is this local Galois representation, and now I have a cohomology class. I know that's not the real way you write the Greek letter Xi, but it's more. I think you all know what that is. So, okay. So If you have a cohomology class H1 of something like this, you can it's canonically associated to an extension, where you have it's an extension of QP by V. So you have this extension. These are all local Galois representations. So on the right, you have a trivial one-dimensional. You have the trivial representation. So this QP has a trivial action. And then there's a way to, from the cocycle representing this, you can write down another vector space that has this kind of extension. Or going the other way, if you have this kind of extension, you can take the element of H0 of this, that's just the number 1. And that will map to an element of H1 of V, and that's what this C is. So if you see, okay? So anyway, there's some correspondence between these things and these extensions. So let this be the corresponding extension. Corresponding extension. And so now I can talk about what it means for C to be crystalline. So I'll call C crystalline if E is crystalline. So because E is just a local Galois representation. Okay, I mean there's another way you can define it in terms of saying it's in the kernel of the map from H1 of V to H1 of B Cris tensor V. You can also define it that way if you want. But okay, anyway, so and now once you have that, you can define the subset of all the crystalline crystalline cohomology classes, and that's what Bloch and Kato define. They denote this way. They put, I'm not exactly sure why, but they just put a little F on there to denote their condition. So that's the Bloch. That just says it's crystalline. So this is just, by definition, it's the set of crystalline classes inside, in this H1, in this local Galois group. Yes?
Is E just some local Galois representation?
Yes, it's just another local. Everything in this is this exact sequence of vector spaces equipped with a continuous action of local.
Extension for there's no reference to elliptic curve or anything.
Oh yeah, E does not have to do with an elliptic curve. Yeah, it's just E is the first letter of the word extension. Yes. Okay. So these are all just QP vector spaces. Of course, it's split as an extension of QP vector spaces. But when you consider the Galois action, then it might not split. And if that's why there's a non-trivial cohomology class there. Okay. So all right. So that's the local setting. Maybe I can mention one other fact now in this setting. So let's see. Okay. So another little fact. So just to interrupt what I was saying so far. So if you suppose you have you have a finite extension of number fields. You choose a place above P, and you have J is an abelian variety again, and you define the V, which is the QP tape module again, and then you can look at the image of this descent map or the Kummer map, whatever you want to call it, the image of the map where you had the local points, well, made into a QP vector space, going into the cohomology. Yeah. So, and then the claim is that the image. I mean, maybe you know that if maybe you study this for elliptic curves, and if you look at a prime of good reduction, and you look at the image of the local points inside the Galois cohomology, you get exactly the unramified classes. So the generalization of that in this case is that you always get the crystalline classes. And if you try to do this at a prime dividing P, where it's good. Oh, maybe this does require good reduction with good reduction at P. Okay, so then this is equal to this H1. Okay. On the other hand, if you choose a prime that doesn't, I mean, here P was dividing this. You might ask what happens when P does divide P, and then everything is just 0. So maybe that's if P does not divide P, then actually this whole H1 is 0. So that's okay. So there's nothing much to say there. Okay, but now let me. So this is all the local stuff. But now let me say how you can give global definitions now of a Selmer group. So this is saying that you have now a way to talk about the image of the local points without referring to the Jacobian anymore, because the image of the local points of the Jacobian can be characterized just in terms of V as the crystalline cohomology classes. And so that's what's going to let you replace the definition of the Selmer group. In the definition of Selmer group, the image of the local points can be replaced by this. And so with that in mind, let me now write down the actual definition of the Bloch-Kato-Selmer group. So, okay, so V is now, okay, so now we're talking about the general setting in the global context. So maybe I can give you some. So this is now we're talking about a global Galois representation, because the Selmer groups are global things. So, okay, so V is now going to be, it's again a finite dimensional QP vector space. But now it has an action of a global Galois group. So it's with continuous GK action, where K is the number field. And so, all right, and now if you have maybe I'll just, as a matter of notation, if I have a global cohomology class now of H1 of K, V, I can get a local cohomology class just by doing a restriction map in Galois cohomology. So I can let this be its image when you restrict to a decomposition group inside the Galois group of K. So then you get a class in here. Okay? Oh, not let. That's not get. Let's see let. Okay, there. Okay, so then, all right, so then you can define, okay, so maybe use blue again. So the Bloch-Kato-Selmer group of this V is this. So its notation will be this, and then you have the Selmer condition, which is denoted by this F, and it's just the set of global cohomology classes that satisfy all the local conditions. But as I mentioned before, the local conditions are there's no condition when you're at a place that does not divide P. So these conditions are really only being applied at the places dividing P, and so then the condition is that it should be crystalline. In other words, it should belong to the local H1F at each of those places. So this should be crystalline for all V's that divide P. Okay, where this P is the same as that P. That's just the rational number P. Okay, so that's the definition. And now, the reason this is useful, this is related to the previous fact about characterizing the image of the local points. Now you can re-express the Selmer group in Bloch-Kato terms without referring to J. So J is going to be an abelian variety over K, and then V is but now it's a number field, and again V is the Tate module. So I'm specializing this definition now to the case of where V is a Tate module, and so then this Bloch-Kato-Selmer group then, which it just boils down to being the classical QP Selmer group of J. Which is great, because now I can talk about the Selmer group using this Bloch-Kato machinery by just looking at V, which only depended on X, because V was defined in terms of the torsion the PDN torsion of J, which could be expressed as homology of X. So this now is all in terms of X. Okay, so now I'm quite happy because now I can go back to my big diagram and fill in some more stuff. So let's go back there. So let's see. I know it's in here somewhere. Okay, so now at this point I can replace this Selmer group by something that I like better, namely the Bloch-Kato Selmer group. So this is isomorphic to this Bloch-Kato thing. And similarly, I can replace. I mean, this thing is by the thing I had before. This is the same as the thing that's cut out by the local Bloch-Kato condition. So instead of writing this, I can talk about H1 of the local cohomology, but with the Bloch-Kato condition. These are the crystalline classes in there. And yeah, there's again. This is just. So these are just subgroups of the corresponding cohomology groups here, and this is just this restriction map, which gives you a restriction map here, and then this. Okay, so then I have maps going here. This local co-boundary Gauss cohomology map. Okay, so now we're almost done. I mean, almost all the bad stuff has been removed. Has been replaced by this green stuff. The only thing that's left to do is to get rid of this tangent space of the identity of this Jacobian. And so for that, there's one more definition that's needed. And this sort of relates to Hodge theory and how you can understand the tangent space of the Jacobian. I mean that in terms of, well, I mean that's the same as. Well, you could take the H1 of the Jacobian with complex coefficients and mod out by half of it coming from the Hodge filtration. And so we're going to do the same thing here. So okay, so let me just define. Well, first of all, there's algebraic de Rham cohomology. H1. I'll just do H1. So H1 de Rham cohomology of the curve, let's say. So this by definition. Okay, so maybe I'll write. This is algebraic de Rham cohomology. So what's the definition? Okay, I mean, when you're doing things algebraically instead of when you're doing things algebraically instead of analytically, you have to use hypercohomology of the de Rham complex instead of just ordinary cohomology because it's. But anyway, so you take the de Rham complex on X, which just means it's a sequence of sheaves where you have the 0 forms going to the 1 forms. I guess it's a curve, so there's nothing beyond 1 forms. But anyway, you would keep going, and then you take the hypercohomology of that, whatever that means. Okay. Well, it basically means you just replace your complex here by a quasi-isomorphic complex that has only injective terms, and then you take global sections, and you take cohomology of that new complex. Okay, anyway, don't worry about that. So and this what is this? This is just a vector space over the ground field over whatever field X is defined over, but it has a little more structure. It also has it comes equipped with a Hodge filtration, which is a descending sequence of subspaces. So Hodge filtration, well, fill, blah, and then okay, so you get a filtered vector space, and then if you want, you can take duals of this to get a corresponding notion of homology, and well, you can guess what the notation for that's going to be, H1, and you have to put the little de Rham somewhere, so I'll put up there, and then that's just defined to be the dual vector space, so the dual of H 1 de Rham. And because this has a filtration, the dual also gets, you have a dual, you equip this with the dual filtration. Okay, anyway, so you get this thing that has filtration, and now I can write down the final result of this whole process that I've been spending more than an hour on. Well, anyway, so now we can finish the rewriting by putting in one more term here. So let me go back to here. And so the thing that goes here now, that replaces this, is going to be it'll be the de Rham homology. It'll be the de Rham homology. But for a curve, this would be by itself would be something that would be 2G dimensional, whereas this is supposed to be only G dimensional. And so we have to mod out by the part half of it, which comes from the filtration. So you mod out by the fill 0 part, it turns out. And then there's a analog of this log. So these terms are getting replaced by these terms, and there's an analog of the logarithm map that's called the Bloch-Kato. So log sub bk, and then this term, just as this was an isomorphism, this sort of curled map here, this one is also an isomorphism, and yeah, and then yeah. So everything is supposed. So now the idea is this part here is supposed to be the. This is all supposed to be the replacement of the rest. So this is good. Okay, so now you can have you can just rewrite the whole thing in terms of maybe I'll try to simplify this diagram just into one diagram, just so the upshot of this whole thing, of this whole discussion so far, has been that in the end we get this new Chabauty diagram that doesn't have any Jacobians in it. So you have x of kp, and now this maps down to this Bloch-Kato Selmer group, which is the substitute for the Mordell-Weil group of the Jacobian. So this is a global thing. On the other hand, you have this local thing, which is the substitute for the group of local points on the Jacobian. And now you want to intersect those two things in here to bound this. And now this, and then there's an isomorphism with this de Rham, this quotient, this sort of piece of the de Rham homology of x. So it's this modulo, this fills 0. And also you can say explicitly what this diagonal map in this picture. This is obtained. I mean, just as this p-adic just as this logarithm map was obtained by integrating p-adic 1 forms, this is also going to be some p-adic integration kind of map. And so, yeah, so maybe I can just write it as, I'll just write p-adic integrals. That's what concretely what these maps are. P-adic integrals. So write down that map. Okay, so that's great. So that's that. Okay, so we're now done with rewriting the classical Chabauty's method, and there are no J's anywhere. So the final thing I want to do in the last few minutes is to show how this generalizes, what Kim did to generalize this picture, because now it's all primed to be generalized. So the idea is here there's homology. And the V itself is, remember, the V is like an étale homology. And homology is like the abelianization of the fundamental group. And so the idea is, well, why not use the whole fundamental group instead of just the homology, instead of just its abelianization? Except the whole fundamental group is huge, and so it's kind of painful to deal with. And so what Kim's idea was to use something that's something that's intermediate, some quotients of the fundamental group that are easier to handle. So. All right, so let me so I'm going to have to do a little bit of group theory to explain what his idea was. So the first thing is the general notion. Just as this is probably a review for a lot of people. For any group, you can talk about its lower central series. So okay, forget everything. So wake up. So let's just take a group. So G is just a group. Okay. Well, maybe it's a topological group. Okay. I don't know. Okay. It might have. Okay. But anyway, just think about a group, and then if you have two subgroups, A and B, you can form the commutator of those two subgroups. So you can let. I'll just write A parentheses A comma B. I'll define this to be, well, you take all the commutators, which are all the elements of the form AB, A inverse, B inverse, such that A is in A and B is in B. You take the subgroup that's generated by all those. Okay, and maybe I should have used a different. Yeah. Okay. Sorry. Topological. Whenever I talk about topological stuff, it's going to be pink. Okay. So you might, if you're doing topological groups, when you're doing topological group, not all subgroups deserve to be called subgroups. Only closed subgroups deserve to be called subgroups. And therefore, well, and this thing might not be closed, so just take the closure there. So, okay. So anyway, that's the definition of the commutator. And then you can define. You can start taking commutators all over the place. You can start with C1 of G, which is defined to be just G itself, and then you can take C2 of G. But it's better to start. Okay, anyway, I'll say this later. You can take the commutator of G with C1 of G, which just means it's that's the thing it's usually called, just the commutator subgroup of G. And then you can keep going. You can say C3 of G. And notice I'm not taking the commutator of the previous thing with itself. I'm not taking the commutator subgroup of the previous thing. That's what you would do for, well, so instead I'm taking the commutator of the previous thing with the whole group. So this thing is descending slower than it would be than if I were taking the commutator subgroup of the commutator subgroup and so on. Anyway, this is going to be a sequence this is going to be a decreasing sequence of subgroups, so of characteristic subgroups in G, and then so they're all normal in each. And yeah, you can just keep going. So that's called this is what's called the lower central series. Okay, so that's this. So that's what this is. And out of this, you can form the quotients of this. You can define also G sub n to be G modulo Cn plus 1 G. Maybe I should say something about the numbering here. So, I mean, the reason for starting with 1 and going 2, 3, 4, if you do it this way, then it has the property that if you take Ci of G, commutator with Cj of G, it lands inside Ci plus j. Like C1 and C1 land in C2. Yeah. So, and the reason for putting n plus 1 here is that this is now, well, I'm measuring the difference between C1 of G and Cn plus 1G. So this is like an n step. This is going to be an n step. So this thing is going to be an n step nilpotent group. N step nilpotent group. And the reason it's called the lower central series is because if inside Gn, you look at the previous group modulo, the image of the previous group. So if you look inside here, you'll have a subgroup that's Cn of G mod Cn plus 1 of G. And that subgroup is going to be in the center of this one, just by the way it's defined. Because you sort of mod it out by all the commutators of that group with the whole group. So you forced it to commute with everything in this. So yeah, so okay, so that's general group theory. And now, well, just as an example of this, you can talk about. So as an example, you can, if you take just G1, so that's a one-step nilpotent group. That's just G modulo the commutator subgroup, which is also called abelianization, G ab. So that's the abelianization of G. Because it's the largest abelian quotient. well, I guess you have to understand quotient in the right sense. If there's a topology, then it's okay. Maybe it's the largest Hausdorff-abelian quotient or something like that. Okay, anyway, so that's G1. So G2 would be the next step, and so on and so on. All right, so that's just group theory, but now let's apply this to the fundamental group of the curve. So let's take, all right, so let's talk about the abelianized fundamental group. Okay, so, well, I mean, first, okay, maybe as a warm-up, let's just talk about what happens over with manifold. So as this is the motivation. So if you start with if you're given M, which is a connected real manifold, say, so, and you also have a base point, and so you have a little m. Well, then you can talk about the fundamental group of M with that. So defined in terms of homotopy class of loops based at that base point, and well, it's okay. That's some big group, probably non-abelian, and you can take the abelianization of it. Yeah. Okay. So okay, maybe I should write. So this thing before you take the abelianization, that's the fundamental group. That's the fundamental group. But after you abelianize it, you get something that's isomorphic to the homology of this topological space with z coefficients. Okay, and now what's an algebraic? Now let's go back to algebraic variety. So what's the algebraic version of this? So, well, I mean, let's just do it for curves, since that's what we're ultimately interested in. So given x, it's a nice genus G curve over K. And again, we need a base point, and if we want to talk about fundamental groups, so let's take a K point. So suppose we have a K point. Well, then the analog of this isomorphism is you have you can talk about the étale fundamental group. I'm not going to try to define it now because we don't have time, but you can take the abelianization of that, and that is the same as some étale homology group. Except now, I mean, because we're not just taking mod p coefficients or z. You can't take z coefficients with étale. You either have to take zp or something like that. And here, except if you really want to get everything, you should take the product over all zp's. You get z hat homology, étale homology, z hat coefficients. And then this, by what we had in the previous slide, this you can also understand as this thing. You can understand as being the if you start with this étale. This étale fundamental group, it's like the G sub 1, where a G is this. Okay, I'm just interpreting it as a quotient in this lower central series. And this thing on the right hand side, this is going to be related to something. I mean, this is going to surject onto. I can just focus on the p-adic part of this. I can just focus on the homology with ZP coefficients, which is going to be contained in the homology with QP coefficients, which by definition was V. That was the thing I called V, that vector QP vector space, and which we also interpreted as QP points of some group variety called fancy V. Okay, so we have this, and so now the idea is, well, I can just change one to something else. So, well, I guess no, I don't want to change all the ones. I want to change that one. And, okay, anyway, so, and we don't want to talk about homology anymore. We'll just deal with the fundamental group itself. Yeah. By the way, all these isomorphisms are all compatible with the GK actions. All right, so I think so So I think I have one more page left, and now so I want to explain what the generalization is to everything. Actually, maybe I should show you where was that page with the upshot. Yeah, here we go. So the idea is this was the original Chabauty, where we translated so as to not mention J. But now I can just write down a straight generalization of this. So this is what Kim did. So now we're going to be talking about deeper quotients of the fundamental group. Compared to this previous page, that was the abelianized fundamental group. But now we're going to look at the deeper quotients in this central, coming from this lower central series. So, okay. So what did Kim do? So Kim. Yeah. So, yeah, sorry for going slightly over. So we're right now at the 15-minute time because we started 5 minutes late, but I'm going to take like 2 minutes maybe. Well, nobody's stopping me. So, okay. So he obtains a generalization where you, of this previous page, where you again use the étale fundamental group, but instead of taking the first, the first quotient, you can go from here to some higher version of the V, and this V is going to be a version of an even fancier V, which is called V sub n. It'll be the QP points of some other variety. And this one is going to be. This fancier V is not just a power of GA. It's not just a power of not just a power of the additive group, but it's an iterated extension. Just as it has a filtration of subgroups such that the quotients are powers of GA, and so that makes this thing. This is going to be then some unipotent. It's what's called a unipotent algebraic group. It's an algebraic group that has a chain of subgroups such as the quotients are powers of GA, or I guess you can define it more to make each quotient equal to GA if you want. Okay, so and you have that, and again it's compatible with the GK actions, and so he obtains that, and also he managed to get an analog of this diagram here. This Chabauty diagram will have a nonabelian analog, and it'll look like this. It'll be more or less the upper part is the same. You have the global points mapping into the local points. And then here you'll have some version of some Bloch-Kato Selmer thing. This is non-abelian cohomology now, since these are non-abelian groups now. So this is not necessarily, this is no longer a group, but anyway, and then you have the local version, and so you have this, everything's kind of the same, and then, and this turns out to be isomorphic by some sort of, you have some de Rham fundamental group, that's the analog of de Rham homology, which maybe somebody will define. It's not me. Yeah, this is my homework for the rest of the speakers, to define all the things I didn't define. So you have that, and then you can take the nth quotient and then you can mod out by, it also has a filtration that you can mod out by the fill 0. And then this thing, and what's also nice is that, you can also describe this map here. This comes, instead of just p-adic integrals in the old sense, these are going to be p-adic iterated integrals, which I think people are going to talk about at some point. And the final thing I want to say, or maybe almost the final thing, is that you also get, and this last row can be viewed as coming from morphisms of varieties, morphisms of QP varieties. Sorry? Invert P in the fundamental, where? Here?
So that map's not surjective in the top row. The image of pi 1 will be a lattice. So on every graded quotient of the lower central series, that maps tensoring in the top line. You've written subjective onto Vn.
Oh, right, because I haven't, yeah, okay, so I really need to do something here, right, to say surjective. Okay, let me not even write surjective, and just, all I really care about, you're right. Because even on the abelian level, you're saying it's not surjecting on, even on the abelian level, it's only like the ZP version. It's surjecting onto ZP, you're right, so, yeah. So, it's, okay, thanks. Okay, so, and then right, so then, the point I want to make here is that this last row here, that these all come from morphisms of varieties. So there's sort of a higher version of the Selmer group, except it's not a group, it's just a Selmer variety. And then there's a higher version of the local Jacobian, which I'll just call J sub n. It is my own notation. And then there's this higher version of the Lie algebra, which I'll call L sub n. So these are varieties over QP, and then the idea is if you have from these morphisms of varieties, you take the QP points of these varieties, and that gives you the previous sequence. And okay, so maybe I'll just end now with the final theorem of Kim, which sort of summarizes how you're going to use all this. So the key, there's a condition you need in order for this non-abelian Chabauty to work, and I mean, classically, you needed the rank of the Mordell-Weil group to be less than the dimension of less than the genus, or equivalently less than the dimension of the Jacobian. But now what you need is for the dimension of the Selmer variety, this is the analog, to be less than the dimension of this higher Jacobian kind of thing. And so if that holds, then this is a smaller dimensional subvariety in here. And then you have, then the x of k will be contained as before in the set of zeros of some non-zero locally analytic functions. Locally analytic functions on the local points of the curve, which will be given by some iterated integrals. And so then, as before, you can conclude that x of k is finite. I mean, there's some non-trivial thing that goes on here. You need to know that the image of this map is Zariski dense. Maybe I should write that here, but this thing has Zariski dense image. To know that when you pull back the functions on this variety to here, that they're still non-zero. So it's Zariski dense image. All right. Okay, so that's it. So thank you for your attention. So I guess hopefully people will say things about these objects in future talks. All right.
We have time for one question.
So many of the constructions you did would work for any variety of any dimension or some Galois representation, and only it seems in the last steps you use that it's curve. So would you get some non-trivial information for arbitrary varieties or?
I mean, well, I mean, there are some cases where people have tried to use Chabauty's method, for example, just the classical Chabauty's method for things like symmetric powers of curves, and some other you can try to apply it for subvarieties of Jacobians. There's some people here who've worked on this. So I know Jackson Morrow and Jennifer. Well, I guess Jennifer Park's not here, but and Joseph Gunter. But yes, I don't know if there are very many other cases where it's actually practical to do something like that. Okay, so I guess that was the only question. Sorry for going a little over time. So anyway.
Let's thank Bjorn again. Thank you.